Well, here we go. We're going to be looking into flux and the divergence theorem. First, I can let you look at a nice video describing flux.
When magnetic field lines pass through a flat surface, we can define a quantity called the magnetic flux that represents the number of field lines penetrating it. If the surface is rotated about the field lines, the magnetic flux does not change. However, the flux does change if the area changes. The flux also changes if the surface is tilted, falling to zero when the surface vector is perpendicular to the field lines. The cosine theta term in the equation accounts for this. When rotated past 90 degrees, the surface normal vector and the magnetic field vectors are in generally opposite directions. Now the flux is negative. Any surface can be built out of many tiny surfaces. So by letting the square become infinitesimally small, we can use calculus to define the magnetic flux through any surface.
And that's what we're doing. Okay, so flux and the divergence theorem. The flux, that is flow of a vector field across the surface, and some of these vector fields, as in the example where the lady with the beautiful voice was talking, could be magnetic fields, as they would be in a physics class, or in physics in general. So, that's the measure of the fluid flow, and you could call it not necessarily fluid flow, but flux in general. So across the surface during a time unit, it's found by summing the fluid flow across small bits of the surface, and that's how the integral, this one, came to be used for it. Okay. Recall the formula came from adding the column of height f dot n and area del s. Okay. And actually the product of the column height f dot n and the area del s of the piece of surface. And this triple integral measures the same amount of fluid flow according to Gauss's theorem, but in a different way. It calculates the amount of fluid flow divergence into when negative or out of when positive small cubes of volume del vi. Notice that the flux of the small cube will be about the same as the measure of the divergence at some point within the small cube. So the flow across the small surface will be about the same as the flow out of some point in the small cube. What happens in the solid itself is that only fluid flow not canceled by adjacent cubes happens on the outside edge of the surface. Hence, it matches the fluid flow across the surface. So, a few definitions. Definition of source, sink, and incompressible. A point in a vector field, x0, y0, z0, is classified as follows. It's a source if the divergence of the vector field at that point is positive. It's called a sink if the divergent at that point in a vector field is negative. And it's called incompressible at that point if the divergence is equal to zero, like a rock. A really good example would be thinking about this. If you have a bathtub that you're filling with water, there's a source where the stream of water coming out of the faucet hits the surface of the tub, right, or surface of the water sitting in the tub. That would be the surface, and there would be a source because more water is being added. And a sink would be if you had a tub full of water, or even if you got water flowing in, you pop the drain, and then the sink at that particular surface, which would be whatever the shape of the tub is, it would be a sink where that water is running out of that surface. And I guess some surfaces, I mean, it wouldn't matter if you opened a drain and the drain contained pebbles and you tried to run that into a rock. Well, that rock isn't going to get any bigger, And if you open the drain under a rock, it isn't going to get any smaller either. So that would be an example of one that was incompressible. So let's look at one more example here in this video. Use the divergence theorem to show that the volume of a solid bounded by a surface S can be given by, look at this. Double surface integral S of x dy dz. Well, by our divergence of the vector field, it must be 1. Why would that be? Because the vector field looks like it'd be xi plus 0j plus 0k. So the divergence would be 1, right? And if we choose f equals xi and let x equal f of yz, whatever that may be, then we're looking at the surface now. Then our normal vector would be I plus the partial derivative of this with respect to y times j plus the partial derivative of this with respect to z times k, all over the square root of, well, we got to make it into a unit vector, so all over that square root, and that should be fairly comprehensible. So our ds in this integral is what you normally see with a surface integral, and so that's going to be what you normally see with a surface integral. Instead of dA, we're going to replace it with dy dz, see, like this. And so the integrand is f dot n ds. So what does that mean? It means, well, here's our f and here's our n. This is a complicated n here. And here's our ds. Wow, what a thing. But now when we dot this and this, you can see that we just get x. And this and this cancel out. So we just get x dy dz. The divergence theorem gives us the fact that this integral that we're just examining is the same as the divergence over the solid Q, which is the same as really the volume of that solid. So these two expressions can also be used to do the same thing, but they'll give us the volume of the solid Q. Much like, think back to line integrals in Green's theorem. We could sometimes find a line integral by finding an area. And we could also find an area by doing a line integral, and that's what this is saying. We can do a surface integral and that'll give us a volume. Or we can do a volume and that'll give us a surface integral. So it's kind of like the two-dimensional version of Green's theorem.